Hi, the ANOVA test is known as the most frequently used statistics. It is a short name of analysis of variance. And in Korean, it is 분산 분석. And 분산 is variance and 분석 is analysis. So when do we need the ANOVA test? We perform the ANOVA test in order to examine the mean difference of samples. In this sense, you may think about the t-test because the t-test is also used to compare the mean difference of two samples. But when the number of samples is more than 2, the t-test is no more applicable. When the number of samples is more than 2, we need the ANOVA test. In other words, we can conduct the ANOVA test also for comparing the mean difference of two samples. So when you have two means to compare, two average scores to compare, technically both the t-test and ANOVA test are applicable. But when the structure of your study has a nature of a comparison of two, such as before and after, or test and retest, the t-test sounds more proper. Moreover, somehow ANOVA test is called as f-test because ANOVA test consults the f distribution for finding the statistical significance. The f-test is comparing the variances. In this sense, ANOVA is one type of the f-tests. But there are different types of f-tests, so it is not correct to replace the ANOVA test with f-test. So don't call ANOVA test as f-test. And in ANOVA test, there are several different types. The types are sorted based on two aspects. The first aspect is regarding the number of independent variables. And when there is only one independent variable, then we perform the one-way ANOVA. So one here indicates the number of independent variable. Then let's look into the one-way ANOVA. We learned that the t-test has independent sampled t-test, and then we also learned paired sampled t-test. ANOVA test also concerns this aspect. When the independent variable was measured, when the dependent variable was measured by independent samples, then the between group one-way ANOVA is a right tool. But when the dependent variable was measured by the same samples or same groups or same people, then the within group or repeated measure one-way ANOVA is more correct. When there is no illustrative word in front of ANOVA, ANOVA alone automatically or typically indicates the between group one-way ANOVA test. And one of the powerful potential of ANOVA test is that ANOVA test is an expandable statistical technique. When we have more than one independent variable, then it becomes two-way ANOVA, three-way ANOVA, and so forth. So 2 here indicates that there are 2 independent variables, and 3 here indicates that there are 3 independent variables. Technically, 4-way or 5-way, 6-way ANOVA are also possible, but a 3-way ANOVA is already complex enough. So my recommendation is no more than 3-way ANOVA. In color study, the 3-way ANOVA is somehow inevitable because, as you know, a single color has 3 independent attributes. So in analyzing the color data, we frequently use 3-way ANOVA test for analyzing the data. So unless it is necessary, a more simple structure is always better. Less is more is also applied to the statistics. But all ANOVA series expect only one dependent variable. That is a common feature. So even 2-way ANOVA or 3-way ANOVA has also one dependent variable. And the 2-way ANOVA has also different types. When all subjects were exposed to the entire stimuli, the within group 2-way ANOVA is suitable. But when the dependent variable is measured by separate samples, the between group 2-way ANOVA is a proper method, or is a correct method. In addition, the ANOVA test can be designed with a mixed model as well. With regard to one independent variable, all subjects are exposed, but with regard to the other independent variable, all subjects are not exposed, then you can design a mixed model for the analysis. So it looks that ANOVA has a complex map. But don't get scared. Once you understand the concept, it is simply practical and no more complex at all. Now let's consider some examples of a situation that are suitable for the ANOVA test. The chart here shows 3 average scores of research methodology classes for the last 3 consecutive years. And the arrow bars indicate the plus and minus standard deviation of each sample. The pink bars should be drawn symmetrically, and the central position are here and here, but the Excel presented me somehow a bit weird, in a weird way. My recommendation for you is to draw the arrow bars and the bar charts rather in SPSS, because out of the same data, the chart drawn in SPSS look more professional. Yeah. Okay. Let's go back to the lecture part. And the average score here are not same, but they look obviously very similar. 3 years of observation is not a long period of time, but still this record provides us an implication that this year would be quite similar. So that will be your story, your interest, right? So let's consider that the last 3 years as recent years. Here we have one independent variable and one dependent variable. What are they? Yes, the independent variable is year, and there are 3 levels. They are, yes, 2011, 2012, and 2013. So 3 levels. And the dependent variable is the grades. In addition, the 3 sample groups are independent from each other because there were no students who have retaken the course. 재수강 in Korean. So there was no 재수강 so far. So what statistic is appropriate to test whether students have received similar grades for recent years? The first hint is the independent variable and dependent variable is 1. So both variables are 1. So one-way ANOVA is suitable. Then the dependent variable grades are gained from 3 different samples. So the data are appropriate for the between group one-way ANOVA test. The basic concept of the ANOVA test is comparing 2 variabilities. As you know, variability, 분산, in Korean, indicates how spread the data are. And it is measuring the distance of every single score from the mean value. Here you are presented with 2 charts. Both have 3 data sets and all seem to fit to normal distribution. And the mean value of 3 data sets is equal, the mean values of these 3 data sets and these 3 data sets are equal. Let's consider or label the total mean as grand mean, the x bar. Then let's try to describe the difference between the upper chart and the lower chart. Compared with the lower chart, in the upper chart, pink, gray, and green distributions are more intensively overlapped. The distances between mean of each data set, so pink mean, gray mean, the distances between these means from the grand mean, so distance between here and this, is smaller than the distances of each score from their group mean. So each score in pink dataset is each score, the distance between each score and the mean. And what I'm drawing is larger than this, for instance. On the contrary, compared with the upper chart and the lower chart, pink, gray, and green distributions are more widely separated. The variability within each data set, so within each group, is smaller than the variability between the groups. For example, the initial score of distribution was like the pink data set. After an intensive tutoring, the improvement is shown. So most of the scores have been moved or have been improved. And when the effect of the tutoring was extremely nice, then perhaps this pink chart can be shifted like the green. In this case, we can consider the effect of tutoring may be statistically significant. In the lower chart, the improvement is perhaps statistically significant, so the shift of the distribution is much more noticeable than here. Well, here we observe some shift from here or from here to there, but still after intensive tutoring, many of the pink group students are staying in the pink score range. So in other way around, when you found one score here, then you cannot yet say which data set this score would belong to, right? However, here it is very obvious that when we know the score, then the membership of this score is the grade distribution. But here, because a lot of portions or a lot of parts of data of 3 data sets are overlapped, so the distinction between the data sets are not clear yet. But here is pretty much clear. Therefore, in case of a lower chart, the fraction or the ratio between group variability over within group variability will be bigger than 1. Statistically, this ratio should be bigger than the criteria value in F distribution. I hope my explanation was clear enough. If you have managed to catch my explanation, I think now you know quite everything about ANOVA test. The ANOVA test consults the F distribution, so we need to know the F value. Here I introduce you how we calculate the F value for the between group one-way ANOVA test because it is the simplest one. The algorithms for the within test and multi-way ANOVA, such as two-way ANOVA or three-way ANOVA, are, I think, beyond our scope. So the ANOVA test is comparing two variability. We put the between group variability as numerator. We put the within group variability as denominator. When this ratio more deviates from 1, in other words, bigger than 1, the stronger the evidence for unequal population variances. In particular, the bigger is the between group variability. The bigger between group variability implies that there was an effect or influence that has shifted the data set with a noticeable amount. Then let's look into the procedure step by step. First of all, don't get scared. I don't ask you to memorize all this. As repeatedly mentioned, my intention is to help you to understand the logic behind. And as far as you can follow me during my explanation, it is good enough. Even if you do not, it is still okay. As long as you know when to use what statistics, you have achieved the goal of this course. Okay, so for those who feel challenged to read all this, let me quickly explain. First, we compare these two types of variability. In ANOVA test, we calculate the mean squares. Mean square means you average the squared values. The squared values are the sum of squared values, and you get an average by dividing the sum through the degree of freedom. So the between group variability is calculated by subtracting the total mean from mean of each group and you multiply the squared mean difference n times. N is the size of a group. But when you look at the denominator of the subtraction, it's between a single score and the mean of the group this score belongs to. In F-test, we need 2 degrees of freedoms. When we refer to the F distribution, you can check it out. The first degree of freedom indicates the number of groups. So if we use the data set, the research methodology class scores for last 3 years, then the K should be 3 because there were 3 sample groups. Okay. And the N can vary because if you as you remember, the size of the class was always different every year. So N1 was something like 20 something and N3 was much less than that, right? Okay. So as this formula explains, the second degree of freedom, it refers to the sum of size of all groups. So you add all size of the groups and you subtract the number of groups and then. Okay, let me show you how we can perform the one-way ANOVA test in Excel. You click data analysis and here you have a list of different statistical techniques and the ANOVA, as you see, is the first place. I think because it starts with A. Anyway, so the single factor means one way ANOVA. And you put the input range. And the group is grouped by columns 1, 2, 3. And output range, let's create output from here. Okay, all right, let's change or reduce the decimal points. Usually I do with number 2. Okay, so column 1, 2, 3 indicates 2011 and 2013. Okay, and this is the size of each sample, and average scores are generally like that, and this should be equal to here. Here I use the function, but if we use this ANOVA single factor test, then it also offers you the descriptive statistics, so it's very practical. Okay, And let's look at the ANOVA table. And here, between group and within group, and sum of squares. So sum of squares of between groups is 0.22, and sum of squares of within groups 22.51. And degree of freedom is 2 because it's the number of samples minus 1, so 3 minus 1, so 1. And this is 57 because if we add these all, then it will be 60, right? So 60 minus the number of group 3, so 57. And this column indicates the mean of squared, mean of sum of squares. So you divide sum of squares through degree of freedom. So 0.22 divided through 2 is 0.11. And here, in a same way, so it is resulted in such a way. And between group variability is numerator, and within group variability is denominator. So you divide 0.11 through 0.39. So F value is resulted at 0.28. And the critical F value or the threshold value is 3.16. So our F value is still within the area that we cannot say that the ratio of between group variability to within group variability is big enough. So therefore, the between group variability is smaller than within group variability, which means that the between group variability is small, it's not big enough. Therefore, the mean difference of recent years is not statistically significant. Now let me show you how we can perform the one-way ANOVA test in SPSS. We, of course, use the same data, and the thing which is unique in SPSS is that we need to put the data vertically. So basically we are handling two variables. The first variable is referring the year, and here I designed this variable in such a way, so instead of typing in the entire number, I I recoded each year as 1, 2, 3. And the second variable is grade. So 1, if you click here and here, then you can check it out. So 1, so the year 2011, there were 23 students, and then another group of students, and then another group of students. So Excel and the SPSS, usually you can simply copy and paste, but like this example, sometimes you need to work for copy and paste to arrange the data a little bit differently. So for between group one-way ANOVA, we need two variables, and the first variable is indicating the group division, and second variable is the dependent variable. And then let's perform the analysis. So you click analysis and the mean comparison, and here one-way ANOVA. This is here is a factor. So the independent variable or the group division, which is year, and as a dependent variable, it's grade. And if you click option, then you can also get the descriptive statistics and the equal variance test, etc. but let's click only the descriptive statistics here. It seems a bit slower than I usually have shown you, because my computer at home is a bit slower than my computer in lab. That's the only reason, not because the ANOVA test is more complex. All right, let's see the result. So should be the same, and as we have seen in Excel, and here also the sum of squares and degree of freedom and the mean of sum of squares. You remember the 0.11 and 0.39, and we calculate the F value by dividing this between group variability through within group variability, and this will result this, and this is much smaller than the critical F value, if you remember. Therefore, the P value is much larger than 0.05. Okay, it should result the identical results as Excel did. I have demonstrated you how we can perform in both Excel and in SPSS.